Okay. So today we are very happy to have Liran Ron from Ben Gurion University, who will be talking about ergodic IRS entropy in SL2Z and free groups. Please, Liran.
Yeah, okay. So thank you for the invitation, and yeah. Okay. So I'm going to talk about ergodic IRS entropy and SL2Z and free groups. Um, I'll start by giving the basic notations that we need, and then I'll talk about the known results and our latest result. So we're talking about random groups. So for us, random group is GMU, a random group, a random walk, sorry, um, where G is a finitely generated group, and mu a probability measure, and a random walk is precisely taking a sequence of IID random variables, G valued, IID random variables with low mu, and then the random walk is the process xt, which is the multiplication of the first t elements. So we think of the u's as the jumps from one point to the next, and the xt's are the steps, our position at time t. Um, so first, I want to define a random walk entropy. So the definition is the random walk entropy of G mu is the limit when t goes to infinity of h xt divided by t, where h xt is the Shannon entropy of xt. And the limit exists. It may be infinite, but for us it will always be finite, and it exists by a subadditivity, Feket's lemma, for any group G and random walk mu, probability measure mu. And the next thing we want to consider is if we have a group G and a random walk G mu, we also get free a lot of other random walks with also their entropies, which is the random walks on the quotients of G. So if we have N, a normal subgroup in G, then there is an induced random walk on G mod N, which is just the process nxt. Just we take xt and we look at the process on the cosets of n. This can be done also for a non-normal subgroup, but the entropy is defined only if we take normal subgroup, a normal subgroup. I mean the limit, which we write the limit, the entropy of G mod n with respect to mu bar, where mu bar is the induced measure, is the limit, just as before, the entropy of nxt divided by t. So for quotients, we also have, if we have let's say, a finite entropy for G, then we also have finite entropy for G mod n for every subgroup, normal subgroup n. But for other subgroups, non-normal, the limit does not have to exist. And so one can ask if there is something more general than these entropy values, and we can take something better, which is IRS entropy. So let's define what is an IRS, invariant, random subgroup. So this is, an IRS is just an invariant probability measure, lambda, on sub G. Let's write it like this. On the space of subgroups of G, invariant in what sense? So G acts on sub G by conjugation. K, G acts on K. This is G inverse KG. So we have an action of G on sub G, and therefore we have an action of G on probability measures over sub G. So an IRS is just an invariant measure with respect to this action. And we think of invariant random subgroups as, like the name implies, like an invariant subgroup. So we can think of it also not like a probability measure, but let's say a subgroup which is not deterministic, but um, um, random, and it is maybe random, but its distribution, as if we think of it as an random variable, its distribution is invariant under conjugation. So if in this notation we think of k as random, then we want that this will be equal to k in distribution. But our definition is just an invariant probability measure on sub G. Now, IRSs are the probabilistic natural generalization of normal subgroups, because normal subgroups are deterministic subgroups which are invariant under conjugation. And this is the analogous probabilistic counterpart. And so we want to consider the same situation where we look on the induced random walk on G mod K, where K is an IRS. It has distribution according to an IRS, and maybe then we can define entropy in a way such that it will always exist for, I mean, in the broad sense, of, for finite entropy random walk. So this is indeed the case. We define IRS entropy. We make the following definition. The entropy of G mu lambda is defined to be the limit, when t goes to infinity, of the integral over sub G of the entropy of k xt divided by t, d lambda k. So we just take a random subgroup and we integrate with respect to lambda, and then we take the limit. And this this limit does exist due to subadditivity. Subadditivity, and of course, we use here the fact that that lambda is an IRS and not just any probability measure on sub G. And in the definition of an IRS, we can think of it. It's easy to think of it as a generalization of normal subgroups in the following way, and this is the basic example of an IRS, the trivial example, you can say. Delta n for n normal in G is an IRS. So the Dirac delta measure over a normal subgroup is indeed invariant under the action, because the subgroup itself is invariant under conjugation, and delta measures are invariant exactly when the point on which they're supported is a fixed point of the action. Okay. So now these are all the definitions that we need regarding entropy.
Liran,
Yes.
can you give one example which is not completely trivial?
Yeah. So the next example one can give is, for example, if we have a finite orbit under conjugation, then we can define a uniform measure on this orbit, and then this will be an IRS as well. And there are other examples that we can think of. One more complicated is the one that we use in our construction, but it is more involved to explain. So now we have the definitions of the entropy of quotient and the entropy of an IRS, and this motivates the definition of what we call the entropy spectra. We have two entropy spectra. One is denoted N G mu, and this is the set of all entropy values of quotients, or which correspond to normal subgroups N in G. This is called the normal spectrum. And the other one is denoted I G mu, and this is the set of all entropy values which come from IRSs, but not from any IRS, but from ergodic IRSs. Ergodic IRS. And this is called the IRS spectrum. So by ergodic, I mean an extreme point in the set of, in the space, the compact convex space of IRSs. Okay, so we're interested in these because these sets are just subsets of the positive real numbers and non-negative real numbers. And if we would not restrict ourselves to ergodic IRSs, then the second set, I G mu, would be less interesting, because one always has you can always take the IRSs which correspond to the trivial subgroup and the whole group, and get by convex combinations every value in between, and the corresponding entropy values are of course 0 and the entropy of the whole group, and this is not very interesting. So we want only values that we can get from extreme points, IRSs which are extreme points in the space of IRSs, not as convex combinations of other IRSs. Okay, so you can ask many things about these sets. For example, are they closed, or are they dense, or are they I don't know, connected? But the most basic question one can ask is, are they trivial, or I mean trivial in either way? Are they just the one or two values, 0 and the entropy of the group, or are they the whole interval in between? Okay, so we have the following chain. One always has these two values, and they sit inside n g mu, and n g mu sits inside I g mu, and I g mu sits inside the whole interval. Okay, so almost everything here is very clear. This is what I just said. You always have two normal subgroups which give you these two values. This containment is because every normal subgroup gives us an IRS. And the last one is because this is true about both kinds of entropy. The entropy of a quotient or of an IRS is always less than or equal to the entropy of the whole group. So so this is the basic chain of containments that we can of inclusions that we have. And the basic question is are ng mu and ig mu simple or full? They can be neither of those, but the basic question is maybe in some cases it is the case that they are just nothing or everything. So simple means just the two values, and full means the whole interval. Okay, so this is our question. And now I want to point out some results about specific groups. So the first one is by Margulis normal subgroup theorem. We get that for G equals SLN Z, where n is at least 3, and G mu is simple for any mu. Okay, because Margulis theorem states that all normal subgroups are of these groups are either finite or finite index, and this implies that ng mu is just has two values, 0 and the entropy of the whole group. The counterpart for IRSs is by Stuck-Zimmer theorem, which gives us that for G equals SLN Z, the same groups, and at least 3, these groups they have a simple IG mu. Of course, having simple IG mu implies having simple NG mu, but this came later, so I stated both of them. Okay, so these are the classical, the more classical results about SLNZ, and then one can ask, this is the main question.
What is simple? It is set N and I are sets. In what sense simple?
What?
Simple. Well, what's simple? What is simple?
Oh, so I didn't write it clearly, but by simple I mean.
What does it mean?
What?
It is not group.
Yeah, I mean this is just a name. Simple means that ng mu or ig mu means that it equals only the set of two values. It's our name. It's not something. Yeah, really. Sorry about that. For ig mu, it's the same. Okay, simple just means there is nothing more than what we can expect to be there always. So this is the case for SL and Z when n is at least 3. And when we know something about SL and Z for n at least 3, then the basic question is what happens for SL2? SL2Z. Because we know that SL2Z is, behaves very differently in many aspects. So a fact that we use a lot is that the free group F2 on two generators sits inside SL2Z with a finite index. Yeah, there is an isomorphic subgroup to F2 inside SL2Z with a finite index. And this helps us, I mean, this can make us hope that if we can figure out what happens in F2 or in free groups in general, then we can apply it to SL2Z, because being a subgroup of finite index means that you are quasi-isometric to the group, and many properties are should be similar or the same. So there is also some things that are known about that. So Bowen, this is in 2014, showed that for G equals FD and mu is the simple random walk, only this specific measure, IG mu is full, is 0 Hg mu. It is the whole interval. So this was the first result in this area, and later on, Hartman and Yedin in 18 showed that for the free groups FD with mu symmetric, finitely supported, we also have the same result. G mu is full. Okay, so these are the two results that were known up to 2018. And so what we need to say about it, these are results about the free group. And when we want to use them to say something about SL2Z, then it's not clear if and how it can be done, because the basic idea is to take a measure on SL2Z. There is a way to push it to a measure on F2 because it's a subgroup of finite index. This is what is called the heating measure, and then we can hope that if we know something about the original measure, then we can say the same thing about the heating measure, and then apply the result for FD to get the result back on SL2Z. But this is not the case for, at least for simple random walk, or more generally for finitely supported measures, because finitely supported measure on SL2Z does not produce necessarily a finitely supported measure on F2. So maybe there is a way to take these results about the free group and lift them back to SL2Z, but it's not very clear how to do it in this way. So instead, what we're trying to do is to get the result of Hartman and Yadin for a wider class of measures. Say for measures mu with some moment condition, and also get some tool to lift it back to SL2Z. Like I said, we start with a measure with this moment restriction on SL2Z. We get a heating measure on F2. Then we know that this the moments are preserved. The moment restriction is preserved. Then we can use the result on F2 and get it back to SL2Z. So this is what we tried and achieved. So now I'll state the theorems, the main theorems of our work. So I'll state it as two theorems. Theorem 1 is just a theorem about a free group. So FD mu has full IG mu for any mu adapted. This means just generating symmetric with finite fourth moment. We don't actually believe that the fourth moment is the best that one can get. It was it basically, in our proof, it has to do with getting a bound about the number of visits to a ball, and the best result that we could get at the moment was fourth moment for our theorem, but we think it can be reduced maybe up to second moment.
What is adapted?
Adapted means generating.
Well,
generating. The support of mu generates the group. So this condition also just means that we want to work on the free group and not on something much smaller, because then it's not, of course, it's not the same properties and behavior.
The moment is on what? On the distance from the root?
Yeah, the moment means the sum of mu G, where G is in the group, norm of G to the, in here to the fourth. And this means the norm of G means the distance to the root, in the distance to the origin, to the neutral element, to the unit. Okay, so I'll erase it. So
Norm is the length of the word. What is norm?
What?
Norm is the length.
yeah, the norm is the length of the word. Okay, so one remark before I state that the second theorem is the proof uses the construction of what we call intersectional IRSs. So this is a you can say a procedure to produce IRSs or families of IRSs. We can write it as IIRS, intersectional IRSs, and I don't think I'll have time to get into it, but this is something of the proof. And this is important when I want to state the second theorem.
Can I ask about the first one first?
Yeah.
So is there a simple counterexample if mu has huge jumps, like exponential jumps?
So actually, I don't know. Maybe Ariel wants to say something about it. But...
Oh yeah, so there's our proof will break down if you don't have second moment. So without second moment, the proof will break down completely. And I think Liran at the end he will say a word about where we use. If he described, if not, then maybe ask again if So there is a place where this moment condition comes in, and it comes up to something to do with the green function of random walks on groups, and it's still open. And if you can improve to the best thing, you will still get the second moment. And to some of the lemmas we use, there are obvious counterexamples. So the proof completely breaks down if you go below second moment.
Mm-hmm.
Can I ask one question? But would you guess the theorem's false without any moment? Not in terms of what you can prove, but do you think the theorem's false?
Yeah, that's a good question, and I don't have there could be a completely, other way of generating IRSs that we haven't thought of, and that this method won't work, even in simpler cases like on lamplighters. Okay. It could be a completely other way of generating IRSs, like Lewis Bowen's method was different for the simple random walk. Maybe you can take that method and use it to construct IRSs and get something else that works with better moment conditions. I don't know.
Okay. So I wrote, I want to write down now theorem 2, and I wrote it in quotation marks because I state it very loosely. It's not like it's not stated formally. The idea is that if F is a subgroup of G with a finite index, any intersectional IRS over F can be lifted. I don't write quotation marks inside this theorem because it's not, all of it is not very precise. Lifted to 1 over G with control over the entropy values. So in other words, two results are one about a free group or free groups in general. And the second one is the way to get it from the free group in our example, from the free group to SL2Z. So that's the importance, but we state it also in the paper as something more general and a way to lift those IRSs from a subgroup of finite index to the whole group, and get still control over the entropy values. Okay, so this is not very this is not stated very precisely, but the corollary is what we wanted all the time. Is if F is F2 and G is SL2Z, then for any mu adapted symmetric with finite fourth moment, the entropy, the IRS entropy values is the whole interval, 0 h g mu. Okay, so this is our result. And of course, there are many things to be still to be said or explained for both theorems. Also, what is this construction of intersectional IRSs, and how it gets all the values, all the entropy values that we want, and how do we prove everything, and also the details of this theorem too. So now what I want to do is to show the most visual and also important construction, not of the intersectional IRSs, but it is related to it, but it is more visual because it uses Schreier graphs. So
can I ask a question?
Yeah, of course.
Maybe you said it, but and I missed it. So why do we want it to be an interval? So what is the benefit, or what do we learn about the relationship between the mu and the group, or something like this, if it's in the full interval?
So the idea is showing either that the spectra are full or simple, is saying something about how simple or not simple the group is, because it shows. I mean, if you have that if you know that you have the whole interval full realization of entropy values, then it shows you for normal subgroups, of course, it shows you that you have tons of subgroups, of normal subgroups. And in the other way, if you know that you have a simple IRS spectrum, then of course you have simple normal spectrum. So the better question, I don't know if better, but the question still to be answered is, what about ng mu for SL2Z? What about normal subgroups? And this is, we conjecture that it should be the same. It should be also full, but we don't know to prove it. So This is the basic. I think this is what I can say. Basic motivation, or what it tells us about the group or the random walks.
Okay, thanks.
Okay. So are there any further questions, or should I go to the construction I want to show? Okay, so I'll tell you what I put in this picture and what is still missing, and then what's it all about. So in the proof we use construction of subgroups of the free group, not normal subgroups, but from these non-normal subgroups we get with the construction of these intersectional IRSs normal subgroups. But we construct some non-normal subgroups of the free group from Schreier graphs. And these Schreier graphs are Schreier graphs which, this is a family of Schreier graphs indexed all by J, such that what they all have in common is the following two properties. The one is that they are Schreier graphs, so they have a root, and the root is right here in the middle of the tree. And we have a finite, they begin like a finite tree, which is isomorphic to the tree in the free group. Here it's the free group on two generators. The tree is a tree of depth J. So it's Bj, the ball of radius J about the root, inside the Cayley graph of F2. So every one of these trigraphs start in this way. And then what we do, we call this a gluing graph. We take every leaf of this tree at the end, and we just attach to it a copy of some other graph. We do this gluing in a way that I will just explain. It is quite simple, such that the whole construction is still a Schreier graph. And because it's a Schreier graph, we know that there is a corresponding subgroup of the free group. We use here the fact that for the free group, it's very easy to construct subgroups from Schreier graphs, because we just need, there are no relations to be fulfilled. We just need to have a Schreier graph with all the labels put right, and then we get subgroups for free. So so I said we have this finite tree, and then we put on every leaf some graph attached to it, and all these glued graphs are disjoint from one another. And what do we want from these graphs to be? We want them to be, as I wrote here, transient and nilpotent. So why transient? Because we want the random walk on this Schreier graph to eventually run to infinity and not return back to the tree. Or more precisely, we don't want it to change the subgraph, the attached subgraph in which it can be. And we want it to be nilpotent. This has to do with the construction of the IRSs, the intersectional IRSs. If this graph that we attach is nilpotent, then we will get that we will have the entropy values, the whole range of entropy values starting at 0. It has to do with that. Okay, so because nilpotent groups or random walks on nilpotent groups have 0 entropy. So we can, if we have, let's say, the Cayley graph of F3, then we can put there, or F3 or above, then we can just put there the attached graphs, can be Z3, Z4, etc. because they are all transient. If we have F2, then we need to take to attach there some quotient of the free group on two generators, which is also transient and nilpotent. Let's say the Heisenberg Cayley graph. So what I want to do now is just to show how I attach for some leaf such a graph. So I take this leaf here. You can see that I need to specify the orientation, but it is attached to an edge which has A or A inverse, depends on how we look at it, in which direction. Let's say A inverse. So I take a copy of my transient nilpotent graph, which is, I say again, a Cayley graph of a quotient of the same free group. So it has labels corresponding to the same free group. And I take an edge, any edge, which has label which is not this generator or its inverse. Okay, so why am I doing this? Because I know that to this leaf here, I need to attach three more edges in order for it to be a valid Schreier graph. So what I do, I know two of them have to be B and B inverse. So I take this edge here, which has B on it, and I just erase it. And now I need to compensate and put an edge which takes me from here to here with a label B. And this is how I do it. I connect this to here and this to here. On this I write B. This should be B inverse. If I write it like this, let's say like this, it's B inverse, or if it's like this, then it's B, not B inverse. So now, I mean, this vertex here has I took from it one edge with label B, so I need to return one with label B, so I did it. And the other one, I took from it an edge with label B inverse because it's an incoming edge labeled B. So I had to give it another edge with label B inverse. So as long as my attached graph, the glued graph, is concerned, everything is fine. I mean, now it is connected to some other graph, but all its original vertices have the labels right. And for the leaf right here, well, I attach to it two edges with B's, B and B inverse, and I still need to attach to it another label with A, because I say here it's A inverse. So the way we deal with this problem is just to attach to it the following graph. This is, you can think about it as a copy of N or Z. We have just an infinite line of edges with vertices. This is a Cayley graph also of Schreier graph or Cayley graph of the free group. And on each one of these, we put a loop. So this is A, this is A, they are all A's, and all the loops are B. Okay, so this is more technical. This is just to keep it all the glued graph now as a Schreier graph of the free group. This construction gives us a Schreier graph, and so we get from it a subgroup which we denote Kn, Kj, let's say, for J. J is the radius of the ball, which we take just to be the ball from the Cayley graph of the free group. And this has the properties that we need. And the idea, it's the vague basic idea of the proof, is that when you take J to infinity, these graphs around the root, they're becoming more and more similar to the free group. And this, in some sense, gets the entropies corresponding not exactly to this subgroup, but to some normal subgroups that we get from the IRS construction. They get them more and more close to the entropy of the full free group. And on the other hand, each one of these Schreier graphs, or each one of these subgroups, we call it locally co-nilpotent, which is just saying that they're always up to radius J, they look like a tree. But then, if you go further, then they look just like nilpotent graphs, either these Z's or these transient nilpotent graphs that we wanted. And all in all, we call it locally nilpotent because for every radius that you want, you can go far enough so that if you look at this radius around you, you can't tell that you are not inside a nilpotent Schreier graph. And this one takes care, like I said before, to the part of the entropy going from 0 up to the entropy of some value, and these values in the other side go up to the entropy of the full group when J goes to infinity. So this was my hand waving about this part. Okay, so we have still a few more minutes. So if there are more questions, and I think this is a good time for me to stop talking about.
Thank you very much, Liran, for a very nice talk. Any other comments or questions?
I can ask one question. You mentioned this result by Margulis for the SLNZ case for n bigger than equal to 3, that all the subgroups have finite or a finite index. And then you said, therefore, you're simple in your sets. Is that implication obvious or easy? Because you could have different indexes of different size.
Yeah, so one side of the simplicity is obvious. It's more or less obvious. It's the part that if your subgroup is of a finite index, then the quotient is finite, and therefore the entropy would be 0 for the quotient. And but the other direction is not so obvious.
Okay, thank you.
Okay.
Other comments, questions?
So I'm not sure if it's completely relevant, but so what happens if you look at a random group? So you start not from a deterministic group, but a random group according to one of the constructions, like Gromov or something like this, right? That you take the free group and start choosing your Yachas Shkilut randomly. So what do you get in terms of these spectra? Is it known?
I don't know. Didn't think about it.
giant groups, property T, hyperbolic, things like that, to small groups, basically. So you jump from, so when you have property T, so this is a result of the name eludes me. Someone from the Technion. No, but I'm having a blackout. So, but anyway, if you have property T, then you have finitely many entropy possible entropy values. So the set I G mu will be finite.
Finite.
Not necessarily simple, but almost simple. And so that's going to be the case in this random relation model of Gomov or things. Typically, that's what you see. And then you jump to finite groups, which is just have zero entropy. So,
okay, thanks.
Any others? Well, okay, if not, let's thank Liran. Thank you very much, Liran. And next week, we have the last talk of this semester and perhaps of this format. So stay tuned and see you all next Tuesday.